Good morning. It is April 8th, unbelievably, April 8th already. Before we get talking about our lesson for today, which is the transfer of heat, I want to go back and do a quick review of a couple of the concepts that we went over yesterday. The first one is how we measure heat. There are two different measurements of heat. One is a calorie, the other is a joule. 1 calorie is the amount of energy needed to raise the temperature of 1 gram of water by 1 degree Celsius. And then the joule is the standard scientific unit that's used to measure heat and to measure energy. And 1 joule is 4.18 calories, or 1 calorie is 4.8 joules. I apologize. So I do want to clarify one thing, because we oftentimes think about calories in terms of food. Well, in actual fact, 1 food calorie is equal to 1,000 calories in terms of how we measure heat and heat transfer. So it's important to remember that calorie in food contains enough energy to raise the temperature of 1 kilogram of water by 1 degree Celsius. Calories in food are 1,000 kilograms, or 1,000 science calories. The amount of energy required to raise the temperature of 1 gram of a substance by 1 degree Celsius is the term we refer to as specific heat, and every single object has a specific heat. And that means that each substance absorbs a different amount of energy to show the same increase in temperature. So if I have a block of wood, the block of wood would require more energy to increase its heat by 1 degree Celsius than would a block of metal. A metal would heat up much faster because it has a lower specific heat. So that's important to remember as we go forward. The other thing I want to talk about is how heat and mass affect each other. So the greater the mass, the greater the amount of energy that's going to be required to increase the heat for that. And this is very relevant when we think about very large bodies of water. And the example I'm going to give you is with Lake Michigan. Lake Michigan holds 4.92 quadrillion liters of water. So imagine the amount of thermal energy required to raise that body of water's temperature by 1 degree Celsius. And that is why it takes large bodies of water to warm up much more slowly than small bodies of water. So those are the two of the main terms that I want you to remember from our discussion yesterday. So today we're going to talk about how we can control the transfer of heat energy. And we do know that there are 3 different ways that heat transfers from one object to another, or one substance to another. And these 3 methods of heat transfer are conduction, convection, and radiation. 2 of these we've talked about before with convection, which is what we have with convection currents within the mantle of the Earth, and radiation, which is the heat that transfers to us from the sun. So as we talk about this, the other main concept to always remember is that heat transfers from a hot object to a cold object. So I'm going to first give you the definitions of each one of these. Conduction is the transfer of heat from a warmer substance to a cooler substance through direct contact. So there has to be a physical connection between the 2 objects for the heat to transfer through conduction. We then have convection, and that is the transfer of heat by the movement of fluids like water and air through currents. Not just fluids, air it behaves like a fluid when we talk about convection heat. And then the final one is radiation, which is the transfer of energy as electromagnetic waves. This can be X-rays, it can be heat from the sun, it can be infrared light. All of those are on the electromagnetic wave spectrum, something we've also discussed a little bit this year. So now we're going to go into more detail. One way in which energy is transferred as heat is through direct contact between objects. Conduction is the process that moves energy from one object to another when they are physically touching. So they have to be physically touching. Conduction, however, can also occur within a single object. And in this case, think about the example if you've got a really hot cup of cocoa, hot cup of hot chocolate, and you stick a metal spoon in it. The part of the spoon that's going to heat up first because of conduction is going to be the part of the spoon that is sitting in the hot cocoa. However, that heat is going to transfer up. It's going to physically touch the hot atoms within the spoon are going to physically touch the cooler ones, and that heat is going to transfer from the bottom up through the metal spoon to the top. So eventually, if that cocoa remained the same temperature, eventually that heat would transfer all the way up so that the whole spoon is the same temperature. When we talk about conduction, we need to talk about two different things, one of which is a conductor and one of which is an insulator. So we can control how conduction works with these two things. Conductors are materials that transfer energy more easily. So if we're actually trying to generate thermal energy, we will be choosing substances that have a very low specific heat so that we can transfer thermal energy faster, more easily, and more efficiently. If we're trying to prevent the thermal heat, we might use something like insulators, and you can talk about even the term insulation, which is up in your attics, which help maintain temperature within your home because they're very poor conductors of heat. They have a very high specific heat. So some insulators are wood, paper, plastic. Plastic foam is something we use a lot with hot beverage cups and stuff, because they can still get very hot depending upon how hot the beverage is, but it takes more thermal energy to increase that temperature, so they're safer for us to hold in our hands. All right, now we're going to talk about convection. We're mostly going to talk about convection in terms of the atmosphere. We've already talked about it in terms of the movement of tectonic plates with the magma that is in the mantle of the earth. And we talked about it a little bit in terms of water with salt and density and how a little bit of how convection works in water. So energy that's transferred through the movement of gases or liquids is convection, and process of heat transfer works by the movement of large numbers of particles in the same direction within a liquid or gas. So they are moving in the same direction. Usually they're either rising or they're falling. Convection tends to work in a circular motion. So when we talk about convection in terms of a cycle of nature, which is really easy to see, we would have cooler, dense air flowing in underneath warmer, less dense air and pushing that warm air upward. When this air cools, it becomes more dense than the warm air beneath it, and it comes back down. And then the cooled air will sink. It will move under the warm air, push that warm air up, so it becomes a cycle. Same thing happens with water. Water heats up, becomes a gas. That gas rises into the atmosphere. It hits up as far as the tropopause. As it moves up higher into the atmosphere, it cools. As it cools, it can condense and drop back down in the form of rain, snow, sleet, etc. So that is convection. Finally, we have radiation. Radiation is the transfer of heat through electromagnetic waves, visible lights, microwaves, infrared light. The sun is our most significant source of radiation. However, all objects emit radiation, believe it or not, including yourself. And I want you to think about infrared goggles. So we put goggles on to determine infrared light. All the spy movies, you've got people seeing at night with night vision goggles. Believe it or not, that night vision goggle is measuring the thermal heat that you put off of your body that's emitted as part of radiation. That's what it's picking up and detecting, thermal heat through radiation. I want you to think about radiation from the sun. You can feel how radiation works. You can feel the heat on your skin. You can feel your skin warming up here in Arizona. It looks to be an absolutely gorgeous day again, and you're going to feel, if you're outside, the heat that's coming to you through the sun. What happens is radiation emitted from the sun will strike the particles in your body and transfer energy. The transfer of energy increases with the movement of particles in your skin, which you detect as an increase in temperature, because at this point the outer air, and remember heat transfers from hot to cold, your body is actually colder than the heat outside, so the heat energy from the radiation is being transferred to your skin, and your skin is picking that up. Sometimes that can be quite unpleasant, and you feel that prickling, that heat. That is where that heat is generated and is agitating the particles in your skin, and it is very hot. Everything can absorb heat through radiation, from air to concrete sidewalks. Everything can have an increase in particle motion, which produces an increase in temperature. Again, here in Arizona, we're very aware of that. Try to walk barefoot on a asphalt road or a sidewalk when the temperature outside has been 116 degrees for a couple of days in a row, and you feel that heat that's been absorbed by concrete. We also rely on that, by the way, in order to insulate our homes. So homes in cooler areas of the country actually choose materials that retain and hold heat. So think about, again, that concept of specific heat. The more specific heat a substance needs to warm up, the more of that heat the more that heat would be generated as they lose it. So we choose insulators in our homes that have a high specific heat content, or a high specific heat, so that we can keep that temperature held within those substances longer, so that helps to keep our homes warmer during colder temperatures. The same can be said of keeping our houses cooler in temperatures, because in terms of retaining the heat, the lower the heat, specific heat, the more things will be held. So that is the primary thing. I do want to talk about the fact that when radiation is emitted from one object and then absorbed by another object, the result is still a transfer of heat through thermal energy. So the radiation is converted to thermal energy as heat. The other thing that I want to specify, that conduction and convection must transfer from one object to another, or they have to manipulate fluids and gases. Radiation is the only source of heat transfer that does not need matter to travel. And I want you to think about this, is that if radiation needed matter to travel, we would never experience the heat from the sun. The radiation travels through space. And remember, we talked about this when we talked about light waves. Light waves do not need matter to travel, and radiation is effectively electromagnetic waves, and that light that's held through there on that visible light spectrum, and infrared and ultraviolet, all of those things are traveling through space, which has no matter, before reaching Earth. So radiation can travel through space. It can also travel through matter. All right? So those are our main concepts for today. You're going to have check for understanding questions. Tomorrow we are going to review a little bit in terms of conductors and insulators. And we're going to go through this a little bit more when we talk about electricity as a source of energy. For right now, though, I want you to come to terms with those three forms of heat transfer. All right? I hope you have a great day. I hope you get a lot done. It's gorgeous outside. If you can, sit outside in your backyards or out in the front of your houses and do some of your work in the sunshine. It'll be good for you. All right? Bye-bye.